and we'll get started. So this is a really good way for us to start back after a holiday. It's a very slow, steady start. And we're entering the unit that's got sort of a notorious name for being very challenging, right? That is calculus. And this is going to take place over chapter 14 and 15. Chapter 14 will probably finish in a week, and then we'll spend most of the work in chapter 15, and that's where the real sort of nuggets are. So, calculus, what's it about? It is about rates of change, okay? It's about how fast or how slowly something is changing. Some quantity is changing per period of time. So, what we're going to start with in 14A.1 is what we call a constant rate of change. Now, we've got, if we're having a look at the top there, we've got a rate is a comparison between two quantities with different units. So, we've got the example down here of water from a hose being used to fill a swimming pool. And so we've got time in minutes, and then we've got the volume in litres. And then we've got a graph of it. So if we have a graph, okay, the rate of change, and we sometimes call that the rock, okay, the rate of change is going to be constant if it resembles a straight line, okay? If we have a straight line, then it will be a constant rate of change. That's the first property. The other way we can determine that is from a table of values. And we can see from the water here, from the water example, it's going up by 15 each time, which means the rate of change is constant. It's constantly going up by 15. So let's have a look at a couple of the examples here. So we'll go through, I think, question 1 and 2, and then I'll let you guys have a go at through. Question 1. The table alongside shows the distance travelled by a jogger at 30-second intervals. Alright, so if we look, we've got time in seconds, so when time is 0, the distance is 0. When time is 30, the distance is 90. When time is 60, the distance is 180. The question is this jogger travelling at a constant speed? So, if we're looking along, we can see that for every 30 seconds, the jogger is moving up 90 metres. We've got 90, 180, 270, 360, 450. Because it's always going up by the same amount, we say yes, the jogger is moving at a constant rate. Okay? Part B, we won't go ahead and do that now. Draw the graph of distance against time, but all you would do, we put time on the x-axis as the independent variable. The distance depends on time, and it would just be plotting those points, and we can see they lie in a straight line. The last one, find the speed of the jogger in meters per second. So there's a number of ways to do this, but what we can basically see is they've moved 90 metres in 30 seconds, or 180 metres in 60 seconds. So all we're doing is dividing the distance. So speed is distance divided by time. All right, we want to know how fast they've been travelling. They've moved 90 metres in 30 seconds, 3 metres per second. Okay, you could take it at the other end as well. We've got 450 metres, all right, in 150 seconds, 3 metres per second. Their rate of change, 3 metres per second, is the same. All right. Part 2, question 2. The graph shows the height of a seedling during its first 10 weeks. All right, so starts off at 10 centimetres, and then it's just getting, it takes 10 centimetres to grow, it takes 2 weeks to grow another 10 centimetres. So we can see that there. Is the height changing at a constant rate? The answer is yes, it lies in a straight line. Because it lies in a straight line, the height must be changing at a constant rate. Okay, part B, find the rate of change in height. Now, rate of change, we're going to make a link between rate of change and slope. Slope and rate of change mean the same thing. All right, slope and rock. All right, how fast is something changing? What's the steepness of it? Now remember, the slope is y2 take y1 on x2 take x1. So we're going to choose any 2 points along this line. All right, any 2 points. So the first, I'll graph this one here. It's like this, right? It looks like this. This first point here has an x value of 0 and a y value of 10. All right, we can see that from the graph. X is 0, y is 10, and I'm going to call that x1, y1. And then we can choose any other coordinate along this line. All right, any coordinate can be at the other end, can be the next one that's very obvious. The next coordinate that's very obvious is here, right? And that has x is 2, all right, we've gone across 2 weeks, and y is 20. So that's going to be the next coordinate I choose, 2 and 20, x2 and y2. And then to calculate the slope, we just plug each of these numbers into the formula. y2 take y1 divided by x2 take x1. Okay, 5, but then we need a unit. Now rate of change is always 5 y per x. What's on the y-axis? Centimeters, the height. What's on the x-axis? Time in weeks. Okay, so we can give it a unit there. 5 centimeters per week. Each week it grows another 5 centimeters. All right, so we've done question 1 and 2. Let's pause there, get you guys to have a go at question 3. So it's finding the rate of change for each function. Now, we know that they have constant rate of change because they're all straight lines. So all you have to do is choose 2 sets of coordinates and find the slope. Okay, so I'll pause there, maybe spend 5 or so minutes having a go at this one.